Hello, Integrated Math 3 and Integrated Math 3 Plus. Welcome to lesson 14-4. We're going to start exploring properties of our logarithms. We've been playing with logarithms. We know they are the inverses of exponential functions. We were playing with how we could write them, how we could turn our exponential functions into logarithmic ones. We've even played a little bit with solving them, and we're going to play with them some more today. We're going to talk about some of our exponential properties and apply them to our logarithmic ones. So this lovely guy over here, old dead white dude, was a Scottish theologian and mathematician, I'll get there, by the name of John Napier. Late 1500s, well before calculators existed. He just felt like people were spending way too much time doing long multiplication and long division, all that kind of stuff by hand. You guys know it takes a while to do these things once you start doing these bigger multiplications and the long division. So he started working on a system that was going to simplify this process. And he basically spent years making these sets of tables that, in fact, allowed you to do large multiplication and large division problems and kind of simplify it down into much simpler addition and subtraction problems so that you could work them out a little faster. Now, of course, this was before scientific calculators became a thing. And so we call this work that he made, these tables that he made, they're called log tables. These days, of course, we use computers and calculators to make these computations. Ooh, I'll get there. But these properties of logarithms still apply. They're still useful. We use them in a lot of scientific applications, and in a lot of later math classes. If you decide to take calculus at some point or statistics, you're going to find that these logarithms and these, more importantly, the properties of these logarithms are going to start to become super handy and super useful. So let's dig in. Now, before we get into the properties of logarithms, we know that logarithms are the inverse of exponentials. So we're going to play around with some properties of our exponential functions first. You already know these, but just to make sure we review a little bit and that you're solid on it. So question number 1 on student activity sheet number 4, right at the top, you have all 4 of these. I would like you to go ahead and review some of these real quick. Keep in mind that b is our base and it's not 0, and that m and n are just integers, they're just whole numbers. So go ahead and hit pause to work these out, a, b, c, and d, and then hit play when you're ready to check your work. All right, so I'm going to bust out my pen here real quick. So a few little things that we should know. B to the 0 power. Guys, anything to the 0 power is 1. You know this. B to the n power times b to the m power. Remember that when you're multiplying two powers with the same base, that you just add together the exponents. So this would actually end up being b to the n plus m power. That if you had b squared plus b times b cubed, you'd have b to the 5th, right? You're just adding the exponents together. Oh, and that means that if we're dividing two powers with the same base, then we're going to subtract the exponents. So b to the n divided by b to the m is actually, hang on, come on, little mouse, play nice with me. Oh, maybe it'll play nice with me. Is actually b to the n minus m. Taking us back to 7th grade a little bit here. And last but not least, don't forget that when you have a power raised to a power, that you just multiply the exponents together. So b to the n power raised to the m power just gives you b to the n m power, that you would just multiply those together. Of course, this is my sketchy writing. I guess it looks prettier there. Fine, I see how it is. Whatever. Just because they wrote it all nice and typed it. Fine. But yeah, you get the idea. Now, of course, please do notice that in order for these rules to work, especially the one where we added our exponents and we subtracted our exponents, the bases have to be the same. If your bases are not the same, this totally doesn't work and it becomes really, really useless. But, you know, for now, we're good. So we're going to play with these properties now that you know them. We'll start off with the first one, b to the 0 power equals 1, because we said any number, any real number other than 0 raised to the 0 power is equal to 1. So what I would like you to do is I would like you to rewrite this exponential as a logarithm. So rewrite this as in logarithmic form and see if you can summarize the logarithmic property in words. Go ahead and hit pause to rewrite it, and then hit play when you're ready to check your work. All right, so first things first, I'm going to rewrite that. I'm going to see if my pen works nice for me now. It's not going to work nice. Haha. So I'm going to rewrite this as a logarithm. All right, so that means this is going to be log, and the base of my exponential is b. So the log of my, so my logarithm is going to have a base of b. Log base b of my argument, which is 1. So log base b of 1 equals, well, my exponent is 0, so it equals 0. Ooh, so this means anytime your argument is 1, it's always going to equal 0. I don't care what the base of your logarithm is. Whatever the base of your logarithm is, I'm going to erase this so we can see it all pretty. Oopsie. Here we go. The log of 1 is always going to be 0. I don't care what the base is. The log base anything of 1 is always, always, always going to be equal to 0 because it's the inverse of this whole anything to the 0 power equals 1 thing. So the log of 1 always equals 0. Yeah, because it's the logarithm. It's the inverse of that lovely exponential property. So this is a cool trick, which I believe answers question 2. So let's keep this going. Question number 3. Let's apply that same idea to b to the 1 power equals b. I know you know this. B to the 1 power equals b. Of course it is. Anything to the 1 power is equal to itself. But I would like you to go to question 3, rewrite it as a logarithm, and see if there's a cool property you can get out of this. Go ahead and hit pause to work that out, and hit play when you're ready to check your work. So first thing I did is I rewrote it as a log. So log base b of b should equal my exponent 1. So I rewrote it as a logarithm. Hey, what does this tell us? Well, this tells me that whenever my base and my argument match, the value of my log is always going to be 1. Whenever I do a logarithm and the base and the argument are the same, the answer is 1. Hey, it's almost like they cancel each other out and you just get a 1 there. That's pretty snazzy. Now, of course, some of our other properties are a little more complicated than that. So this is going to get a little funkier. So for question 4, I want you to have a pencil in hand ready to go. And I'm going to walk us through this step by step, but you definitely want a pencil in hand. So remember what we said, that when we multiplied 2 exponential expressions and the bases were the same, we got to add together our exponents. So we're going to see how we can work this out with logarithms, and it's going to be super cool. It's going to get messy first, though. So like, for example, you know x squared times x to the 3rd would, of course, give you x to the 2 plus 3 power, but we usually just write that as x to the 5th power. So you know this is not a surprise to you. As long as the bases are the same, you can add together their exponents. A -5 and a 2, that's going to give me y to the -3 power. Hey. So none of that is a big surprise to you. What we're going to do, though, is we're going to try to convert this into logs. Now, right now, this is a little terrifying to try to convert it into logarithms. So we are going to go ahead and we're going to see if we can do a little bit of substitution here. And again, it's going to look a little funny. It's going to look a little funny, but this is going to help us answer questions 4 and 5. So it's going to look really weird before it gets really nice, okay? Don't panic. Have your pencil ready to go. So just to simplify things a little bit, I'm going to say, okay, instead of b to the n power, I'm just going to put in a p to make it easier to write with. And instead of b to the m power, I'm going to put in a q, just to substitute in, just to make it a little easier to work out, you know. I can write the logarithms of these guys, though, right? I mean, I can totally rewrite that as a logarithm. I can rewrite the other one as a logarithm. Yay. So we used p for b to the n, we used q for b to the m, and of course, then I could rewrite this as a logarithm. P equals b to the n power, well, that's just log base b of p equals n. And same thing here, log base b of q is going to equal m. So I have an n equals and I have an m equals. Yay! Because again, trying to write the log from this was scary, but I can write the log from these little guys. I can break it down to pieces. That's cool. So what we're going to do is we're going to substitute in P. We're going to substitute in Q. Again, just trying to simplify things just a little bit, just trying to simplify things a little. And then I'm going to rewrite it as a log. Okay. So I went ahead and I tucked in P and Q just to make it easier. And now that I don't have exponentials on both sides, I can rewrite it as a logarithm. So log base B of my argument, which is P times Q, equals my exponents, which was N plus M. I bet you can guess what we're about to do next because you see it up here, don't you? N equals, M equals. Yeah, you can tuck those in and replace them. So I'm going to do that. So instead of n, I'm going to put in log base b of p. And instead of m, I'm going to put in log base b of q. There we go. Look at what we have here. So we've done question 4. We're now ready to answer question 5. Check out what just happened here. This means if I've got a log of two things being multiplied in my argument, I can actually split it up into the sum of two logs. Now notice my base never changed. And all that happened is that my argument, because the two things in my argument were being multiplied, I can rewrite them as a sum of two logs, which is a cool trick. And if you're writing this down for question 5, which I hope you're writing down for question 5, it doesn't leave a lot of space, but just, make a little note there of what we call the log sum property. Now, please notice, in order for me to be able to rewrite them as a sum, my argument, the two pieces of my argument have to be multiplied together, all right? This is such a cool property. I don't know if you even realize how cool a property this is. We'll be able to take advantage of that in the future, but this is a super cool property. So if we can do this for multiplication, what do you think happens with division? Oh, so we're going to do question 6 and 7 again. I hope you've got your pencil ready. And again, we're kind of starting off here where we started off on the other one. So just to simplify it, because trying to rewrite all of this as a log when I've got exponentials on both sides is, well, terrifying. So we're going to replace this. We're going to substitute instead of b to the n, we're going to call that p. And instead of b to the m, we're going to call it q, just like we did last time. Just like we did last time, I can rewrite p equals b to the n power. I can rewrite it as log base b of p, and that's an n equals out in front. And same thing here, my exponent alone, m equals, and I can do log base b of q. And again, I can substitute in for b to the n, I can substitute in a p, and for b to the m, I can substitute in a q. And again, this just helps us out a little bit, makes it a little easier to write these things. You know what's coming next. Now that I only have an exponential on one side, now I'm going, again, we're still on number 6. I'm going to go ahead and rewrite this whole thing as a logarithm. So log base b of p divided by q equals my exponent, which is n minus m. I know you know what's coming next because we know what n equals. N equals log base b of p. I can substitute that right in there. And we know what m equals. M equals log base b of q. So I can substitute those guys in there too. Bam. Shoving it in. Substituting the other one in. There it goes. That's right. Hey. We called that last one the log sum property. What do you think we call this one? Let's fill this in on number 7. What do we call this one? Come on. It's the log difference property. So the log of a quotient is equal to the difference of the two logs. So if I have two things in my argument that are being divided that are a quotient, I can actually rewrite them as a difference of two logs. Please notice the top guy is always in front, the bottom guy is always at the back, and that's a minus sign in the middle. You got to watch out for that because, of course, we know that subtraction matters. So you got to be careful. Real quick, can we bring this back to Red and his fire ants for just a moment here? Remember when we were playing with Red and his fire ants and how in the last lesson we got two different logarithmic equations to solve the exponential function? So we were given that we had the exponential function 20 times 2 to the w power because 2 is our constant multiplier, constantly doubling the number of fire ants. And 20, because 20 was our initial amount, we started off with 20 fire ants. We rewrote this as an inverse function. So we divided both sides by 20 and then rewrote it as a log. So log base 2 of f over 20 should equal w. Again, this is all back to last time. But do you also remember that we were playing around with the graph and we noticed that we could do it instead, that we could just do a vertical shift on it. And so we had log base 2 of x minus 4.32, that this also gave us the same graph. And we were like, wait, why does this equal this? Can we talk about that for just a moment? Why are both of these the same? Why are both of these giving us the same graph? Well, guys, check it out. You now know the log difference property. You could actually rewrite this as log base 2 of f minus log base 2 of 20. The log difference property lets us do that. So instead of log base 2 of x over 20, I can do log base 2 of x minus log base 2 of 20. If you were to grab a calculator, and we'll talk in later lessons about how to make your calculator play nice, but if you had a way of calculating that out, what you would find is that log base 2 of 20 is about 4.32, which is the amount of vertical shift that we found on our transformation. How's that for trippy? It's not exact, but this kind of gives you an idea of why that happened in the last lesson. As we continue, we're going to play a little bit more with some of these properties and how we can get your calculator, and it doesn't have to be a fancy calculator, just any old plain scientific calculator, how it can actually do what we want it to do and solve this stuff for us. But in the meantime, guys, I hope you found this helpful and I hope you found this useful. If you have questions or concerns, please feel free to email me or come see me during office hours, and I'll see you soon.